Okay, let's finish up with the rest of our lecture 2 here. We're going to go through some scheduling algorithms around CPU scheduling, and what we'll find in this section is a lot of things that will be repeated, I think, as we see other issues come up around, ways of doing memory management, a little bit in file systems, but really getting to a point where we can kind of understand in a computing device how we would think about logistically some algorithms around that. And so we'll talk about them. I'll kind of draw out the good and the bad of each one. So again, I use this word fair all the time, but I think it's really making it seem like you're the only one on the system. There's nobody else there. It's just you, and that's the way it should react. The reality is, if there was a lot of stuff working in the background and taking up all the CPU, and you couldn't see the screen, or you couldn't type anything from the keyboard, or it was really laggy, obviously that wouldn't work. So really our goal is to make it seem like you're the only one on the system. When we think about different systems, I'm going to skip the batch run there, but if we think about interactive or real-time, there's obviously differences there as well. It might be that in the interactive piece of it, we're actually focused more on kind of that idea that it's only really there to respond to me. So there shouldn't necessarily be anything else really working in the background. So if you think of like a Nintendo or a gaming console or anything like that, I mean, it's really there to ensure that we're up to speed. And can you imagine a racing game or anything where you're a second behind everybody else in the game? It's unusable. Real time are also forms of that, but used in different forms and needed in different ways. So I think when we think about real time, it's really more around things like smart cars, smart cities, anything that would be something where it needs to happen exactly at the millisecond it actually happened, instead of it being something that can spool or batch up. So here they come. Here's these algorithms, and they're always kind of the same, and we always kind of start with the same few. And again, you could think of this again in that grocery store example that I keep talking about. First come, first served, shortest job first, shortest remaining time next. There's many, many, many more we'll be talking about. But I think as you look at these and you think about how would you schedule something that's fair, we kind of always tend to go back to our human analog life and think about what would be fair? What would be fair at the grocery store? Would it be fair that the first one in line gets served first? Well, sure, but because we have emotions and, I was there first, and entitlements and all that fun stuff. But, the reality is, in a computing world, there are no emotions, and there are, no real competing agendas. We're just trying to compute things as fast as we can. So the algorithms we think about usually go beyond this, and they get into different modes of figuring out how can we make it all, kind of run at the same time, or at least make us feel that way. So we'll go through some of these, but just keep in mind that most of these do have either a major element that makes them not work, but we always kind of start thinking in the same modes. So it's very easy to draw out some examples of how this works, but more importantly is really how it doesn't work. The problem with shortest job first is that you first have to know how long all the jobs are. So I don't know how many developers out there know exactly how long a function or method's going to run, how long it's going to take, how much CPU time it's actually going to use. So it's pretty hard from the beginning to even think about how to do this. But if we did have a mechanism to know this, that they are in this order, what we do is we put the shortest job first. The problem that comes to this is another thing that I talk about quite often in this class, which is the difference between the Democrats and Republicans. And what I say about that really has nothing to do with politics, so don't worry about election years and who likes who. I'm not talking about that. I'm just talking about the thought process around, the Democrats are usually more focused on, more, everything equal for everybody, and Republicans are usually more about, those that, work harder, make more money, whatever. Again, not getting into politics, but if we start to think about things in priorities, And that's kind of what this is here if you think about this in a very long, time duration. We are kind of putting a priority on things, right? We're saying the shortest job goes first. Well, what happens to the long job? Does it ever run? You could keep arguing that if I reevaluate this at every time a job gets done, the long job might never get done. So that's a big hindrance and a big reason why this kind of doesn't work, aside from the fact that we don't really know exactly how long these things are going to run. These are all very, very common ways to do scheduling, and actually round robin is part of what we do today in kind of the modern versions, just because it is kind of the easier model to kind of go around and say, okay, if it's your turn and you have the CPU and you need it, then you get it. And so we'll talk about that in a second. Priority I just talked about. Multiple queues is actually, again, a bigger kind of piece of this, because it isn't necessarily that it is that it works that well to have just a single queue. Shortest process next is just about the same thing as what I just talked about. Shortest job first, same thing. Guaranteed scheduling. Again, if I bring in the atomic operation kind of concepts, then I'm kind of making bad things happen. But could I guarantee that your service is met? Well, maybe. It depends on what you're doing. A lottery or just random scheduling, fair share scheduling, and this goes on and on and on. And so there's many different ways to think about it, but it is a very complex way to think about how it renders itself in value today. Round robin is pretty straightforward, right? You pick a point and you just keep going around and you keep saying, A, B, C, D, A, B, C, D, A, B, C, D. In this example here, this is just kind of showing that, it goes B, F, D, G, A, so on and so forth, and obviously moving them around. Priority is, in a couple different ways. It could be that everything that has the highest priority goes in a queue. I think a lot of people think, well, it's just the one that has the highest priority. Well, usually you don't rank them in that order, but the reality is we'll see in a little bit that operating systems actually do have to put things in, highest priority and lowest priority. Pretty granular, but still we need a queue, and that's what's kind of showing by the runnable processes there. But again, priority begets what's called starvation. Priority ones might never go. So is that fair? Time. Time is the thing we're against the whole time. So when we think about programs running, there's a couple things we need to think about. One is how much CPU you have at what times, how much I/O wait are you doing, but as importantly, how did you write your code? Did you do a sorting algorithm that was really not the most optimal? Did you use for looping that could have been done magnitudes faster, done a different way? We could take that in the databases. Did we write a SQL query that was sub-optimized? Could we have put databases together, unioned some different things together to give us faster output? So there's a lot of things that go into really around the scheduling. And when we talk about real time for this as an example, that's where a lot of this stuff kind of goes away, and we have to almost get down to the nitty-gritty of not relying on subsystems and really just having the critical components right there at our fingertips. We talked about thread scheduling before, and I think the key to this is that are we CPU scheduling based on processes or based on threads? And the reality is you have to do it based on threads, because the threads are the most atomic unit of process now, because if I have 1,000 threads in one process and one thread in another process, it's not fair to treat those processes the same. We have to actually treat the one with 1,000 as 1,000, and the one with 1 is 1, and so we have 1,001 threads running, and how do they get kind of dulled out for CPU? So same kind of thing, same idea. one of the things that is key is knowing how your threads are managed through your kernel. So are they one-to-one, one-to-many, many-to-one, many-to-many? Because as they get chosen to then kind of run, is there a lot of context switch in moving them around and connecting them through and making them run? So just you as a developer really needs to kind of dig into that if threading is going to be a form of concurrency that you really want to, make something happen in a tremendous amount of speed. Now, this is a very common problem that we talk about, and I'll add one hitch to it. This diagram is wrong. The fact that they're forks doesn't make any sense, because the real dining philosophers is chopsticks. You need 2 chopsticks to eat food. You only need 1 fork to eat food. So, I've sent this one in as a bug to the book as well. But forget the forks. Pretend that they're chopsticks. The idea really is an algorithm around what would happen if you were going around and you said, okay, only one person can eat at a time. So what you would do is you would basically create an algorithm that would say, if hungry and you've got your chopstick to the right and left, then you can eat. And you eat for a certain amount of time, and then you put yours down, and then the next one goes, and then if the next one says, well, I'm not hungry, and then just skip it, move on to the next one. So this is just a form of how we can think about CPU scheduling. Again, it doesn't work with forks. So this is kind of that idea. So the idea is that when you're not eating, you're thinking. So it's a little better than saying sleeping, which is what our processes do. But so as we kind of go through the 5 philosophers, the 5 processes that are looking for food CPU scheduling, we're really going to kind of go through this and say, I'm going to take my fork on my left, I'm going to take my fork on my right, or however you want to think about it, on your right and left. And once you have both of those, which those are blocking calls, but when I have both of those, then I eat. And I eat for a certain amount of time. That's not really kind of set in here, but each should have a timer on it. Because otherwise you could eat until you're done, and then you go away, and that kind of defeats the whole purpose. As you put the forks down, or the chopsticks down, then it kind of rotates to the next one, and we keep moving on and on. And you can take this a little further in just thinking of it a different way. And then this one actually using mutexes, which is a better way to do it, which gets rid of some of the race conditions that would happen if somebody was putting fork down as somebody was picking it up, and maybe they had put their other fork down and still eating, whatever. Doesn't fit perfectly in this example, but you get the gist of it. So again, just kind of finishing this whole thing off. Now we've got the reader-writers problem, and this is another one. So dining philosophers, reader-writer, there's a whole bunch of pretty common things that we need to think about. And this one really is again around looking at the difference between who is reading and who is writing. And again, the problem only ever comes in if somebody wants to write. So if we think about the whole concept that everybody's reading all the time, no big deal. That doesn't really change anything. But when the first person comes in, or the first process that comes in and wants to change something, modify something, write something, that's where we have to think about, well, what do we do to the readers? Do we tell them to stop? Do we tell them to rewind? Do we tell them to go back to a sane spot because of what we're writing? So it does become a difficult problem. In database theory and in practice, there's a lot of this where sometimes when you update databases, some databases actually support that you can update all the way down to just a single field. Some are records, some are tables, and so you get those things locked out depending on what you're doing in a reader-writer kind of idea. So how we think about that is really how we have to figure out what that means to us. So writer comes in, basically has to get to the point that it's getting that exclusive access to it. And this one is not taking the algorithm far enough to say that the reader can just stop at any moment and then start again. Because what if you just change what they are currently reading? Then it becomes kind of obtuse or wrong. So just another way to look at it. So we'll revisit a lot of these coming up again when we talk about memory and when we talk about some other core components. But with that, I'm going to stop this recording.